Okay, so with a buffer, the pH of it is whatever it's trying to regulate at. Now, the tricky part here with a buffer is made by mixing two things together. One way I'd say is a true mixture, because you're just a salt and a weak. They're not really reacting with each other. It's not a chemical reaction, but by adding the salt, you increase that A minus. The other way is to do a strong with a weak, right? Strong acid, weak base, or strong base, weak acid, with the same concept of we need to increase the amount of the conjugate pair, okay? So there's actually the long way to do this to find the pH of a buffer is to actually do like multiple rice charts and then combine them together because they're reacting. But there's a quick way with this equation we're going to show you, but that's kind of like, in a sense, how this equation was derived is through that process. So this equation is on our formula sheet, so we don't need to memorize it. We just need to know how to use it. Okay, so, excuse me, the equation is that the pH of a buffer, now keep in mind, this equation is only for buffers. Don't try to use this equation on a non-buffer solution. Okay, so the pH of a buffer is going to be equal to the pKa of the acid. So let me get a drink here. Where the pKa is taking the negative log of the Ka. And the Ka, this is going to be given in the problem. Because this is like unique to every acid, right? Every acid has its own K value, which is its equilibrium constant. Okay? We take the pKa of the acid plus the log of the ratio of the two key parts of a buffer. So what are the two main things in a buffer? Yep, so it's the ratio of HA to A minus, because that's what we care about. Now, this one we just wrote, this one is on our formula sheet. If by chance you were working with a basic buffer, so this would work only for acidic buffers, because notice A means acid, so Ka is an acidic buffer. If instead they gave you a substance that was a base and had a Kb value instead, we have to change the equation a little bit, and that one's not on your formula sheet. So let's think about some ways you could go about doing this. So instead of pH, what would it find if it was for a base? Yep, so the equation would start POH. So keep in mind, once again, this one we're writing is not on your formula sheet. So try to see how you can take the one given to make it what you want. Okay, so it's POH because it's a base is going to equal, what would be the next part?
PKB.
Yep, just the PKB, which is still going to be given in the problem. Plus the log. Now, what are the two parts of a basic buffer? It's not OH. So one is the base itself, which we call B. There it is. Brian, I think that was you in the back. It's the conjugate it makes, so HB plus. So once again, this right here, this one is for if it's a basic buffer, and it's not on your formula sheet, but hopefully you can see how you could look this up and then translate it. Kind of just do the opposite of each of the pieces. Yeah, Brian.
Is it supposed to be for the base one that HB plus on top of the is on the bottom, and for that acid one that
It is, yeah. So always the conjugate pair of the original is the one on the top. Because it's like the base is, does that make sense? Good question though. Any other questions before we try a problem? Okay, let's look at first actually, before we try a problem, we're gonna look at what this ratio represents for us, which would come into play a lot with multiple choice questions. So even though you're allowed a calculator on the multiple choice part, a lot of the questions are designed to not need a calculator. They're just understanding it big picture wise. So does anybody know, and if you don't know this off the top of your head, it's fine, but does anyone know from learning logs how to get log to equal 0? The log of what equals 0? Yeah, so for those that haven't ever learned logs yet, if you plug in log of 1 in your calculator, you get 0. So if my ratio here is the same, that must mean that the amount of A minus floating around is the same as the HA, because that's how the fraction would be 1. Because if the fraction is log of 1 would be 0, and so then the pH would simply equal the pKa. Now, of these two things floating around, the HA, this is kind of the acid part of the buffer, right? Because HA is the weak acid, while A minus is the basic side of the buffer because it's the conjugate pair. So now, if we're looking at this next scenario where we see a problem where the pH is now less than the pKa, if pH gets smaller or goes down, is the solution becoming more acidic or more basic? Good, so this would mean it's become more acidic than it was before in terms of making the buffer, right? Whatever the acid was at, we've actually lowered its pH when we've made the buffer. So which species would I have more of if it's more acidic? Good, right? Does that make sense? That you're going to have more HA, so A minus is going to be less than the HA because HA is the acidic side of the buffer. And then reverse that, right? If the pH is greater than the pKa, then that means it's become more basic. And so that means we must have more A minus than we do HA. Okay? Yeah, Alex.
Would it become, there's probably something I'm just not quite clicking yet, but is there, if there was less HA, would that mean it'd be more acidic because it broke apart and now there's more H plus?
So keep in mind, the HA is always weak, so it doesn't break apart very much at all.
Okay.
But it does break apart to some extent, and so that's why there would be more H plus, and so that's why the pH is lower, yes. But just make sure to recognize most of the HA stays together. But if you have a higher percentage of HA, you're also going to have a higher percentage of H pluses as well.
Yeah.
Does that make sense?
Yeah.
Okay. Let's take a look right here. So this is an example from an AP test on applying this concept. So this is, once again, there's the concept. Here's how it would look on the AP test. It says, a student pours 10 milliliter sample of a solution containing H2C2H3O2, and it gives us a pKa value. Okay, right there, as I'm reading this question, I would say, okay, this is a weak acid. How do I know that? Has an H in front. It's not on the list. And how do you know that?
Because they give us something telling us how far it went.
Good. That, honest me, is the biggest context clue. If it has a Ka attached to it, it's a weak acid. Strong acids don't have Ks. And if it was a base, it would have been Kb. Right? So really, that to me is the easiest context clue, is if a problem gives you a Ka value, you know it must be weak acid. Okay? All right, we have that weak acid, and, okay, what would we identify? What's this thing here?
Salt.
Good, yep. Sodium's kind of those ones you see it and you're just like, it has to be a salt. There's sodium, right? All sodiums are salts. So, once again, keep in mind, we know it's a buffer question because we're talking about buffers, but notice in this whole question, it never said the word buffer. So we need to be able to, as you're reading, identify, hey, weak acid salt, they've made a buffer. Okay? It then tells us we add a few drops of this indicator and observe a yellow color, which indicates that the pH of the solution is less than 3.8. And we are trying to say which of the following is true in the beaker. So the first thing I'd recognize here is the pH less than or greater than the pKa? Yeah, so this is less than, right, the pKa value. So if pH goes down, that must mean, is it more acidic or more basic if pH goes down? Right, so more acidic. And so which species am I looking for is there's going to be more of? Yep, more HA, which is A. All right, so more acidic means more HA. questions on kind of the thought process of that question? So once again, that's kind of on the multiple choice side of things. I've seen a lot of variations of this same type of question throughout the years. Okay, all right, now let's get to a more FRQ, maybe multiple choice, but actually using the equation as it's written. Okay, so flip over to this one. Oh yeah.
Really? That's so nice.
All right, so using this equation, the key thing is we need to, they're always going to give you the Ka, which you can convert to a pKa. Then you need to identify the A minus and the HA. The first thing we want to do when we read a problem is to identify what type of buffer is being made. Okay, so don't say it out loud. I want you to see if you can identify. Read this on your own and see, is this a strong, weak buffer or is this a weak salt buffer? Don't say it out loud, but write it on your paper what you think it is. Is this a strong with a weak buffer or is this a weak with a salt buffer? Give me a pencil drop when you're done deciding that. Once again, identifying the type of buffer is going to change our solving approach. All right, if you said that this is a weak and a salt buffer, have a smiley face because you're correct. All right, so lactic acid is my weak acid. There's a Ka value once again, so I know it's an acid. And then what's the salt that it's mixing with? Sodium lactate. Which, I'll be honest, maybe, I don't know where I got this problem from. I feel like they probably would have given you the formula for sodium lactate. But once again, hopefully you can see sodium, the lactate is that common ion with the lactic acid. Okay, so when it's a weak to salt equilibrium, the setup is actually pretty straightforward. So our equation is pH equals pKa. So we need to take the negative log of the Ka value, which they gave me. All right, so that just came from there. So take the negative log of the Ka. Now pay attention. Some problems might just straight up give you the pKa. So you don't have to take the negative log. So be aware that you don't take negative logs of things that are already in pKa form. Hint to future problem. Okay, plus the log of A minus over the HA. So the A minus in my problem up here in our formula, when it's a salt weak relationship, this is always the salt, the A minus. Because the salt breaks apart, creating as much A minus as the salt you put in. Okay? While the HA, oh, that's not a highlighter. So the HA here on the bottom, this is always the acid. So on top I would put 0.10 because that's how much salt the problem said. And then on the bottom I'd put 0.12 because that's how much acid it gave me. And then at that point, make your calculator do the work. I would practice typing it in so we can make sure you understand how to type things in with logs. Because I'd hate for you to know how to do it but get it wrong because of calculator. Yeah. What do you normally use? Do you normally use a graphene? Okay, use this one. That way you can kind of practice on something you'd like use on the test. If you type it in correctly, you should get 3.77. So try that out. Let me know if you have any calculator issues.
I haven't done it yet. You did it. I will.
3.77 is what I got.
I got that too.
I mean, the process is sitting
And if you don't get that and you don't know what you typed in, let me help you or someone else. 3.77?
I have it.
I got 2.77.
That's peculiar. You did it in pieces, but I can't tell what's wrong with your pieces.
You're not gonna like shouldn't it get to the same.
Yeah.
Break it up.
As I'm just trying to figure out like if something got just like typed in wrong.
Yeah, if you do them. Oh, something happened right there.
Oh.
Oh, I got it.
You
Figured
did
it
10
out.
and
Yeah.
E. Good find, good find. Yes.
I just. I'm like, wait. That looks different.
Phone calculators are the worst. For how smart Apple is, you think they'd know how to like make a better calculator. Try this one. Okay, if you got 3.77, go ahead and move down to practice 8.9 and try this one as a table. Let's see if we can do the whole process on your own, okay? Ready, set, go. 8.9.
I thought it was a make it.
All right, 3 minutes and then we're checking our answer to 8.9, the practice problem.
Wait, so how?
Yeah.
So, if this is given a Ka, can it still be a weak base?
Nope.
So
If
it
it's an
has-
A, it's an acid.
If it's an A, it's
So
an
we
acid.
just
So it
know
doesn't
it's a
matter
weak
if this.
acid.
Because it gave you
Because of
Ka.
that. Okay.
Yep, this
Okay.
is one of those weird formulas that goes against all the rules of like looking at it, of knowing it's an acid.
And then-
So thank goodness they give you a Ka.
Yes. And then with this one, if it is OH, then would this be a weak base? Because even though it already has that Na. So,
Do weak bases ever have sodium or metals?
no. Oh, they don't. Oh,
Yeah,
okay.
weak bases never have metals.
We
Weak
see
bases
that
never
it
have
has
metals.
one metal,
Okay.
is it just kind of like a telltale that it's a salt?
Unless it's one of the strong bases. But
Oh,
yeah,
so strong bases have metals, weak bases don't.
yes.
Okay.
Yeah.
That makes sense.
Does that help?
Yes.
Oh, okay. Wait, but how would we know if it's a strong base or a salt base?
So strong bases are first two columns of metals with OH.
Oh wait, really? That actually makes it so easy.
Technically, I think beryllium hydroxide isn't, but everything else is. When you think you have an answer to 8.9, raise your hand and I'll come give you the stamp of approval or try again.
There's still non-real answers. So.
No, oh dear. Yes, Evan. That is it. Good job.
Bang bang.
Good job. Have a smiley face. Good. Have a smiley face. Well done.
We'll figure it out.
Good. Have a smiley face. That's the answer.
What if it has a PK?
Yeah, 3.74.
Good. Have a smiley face. Good job, guys. Good job, Caleb. Have a smiley face. Good answer. Have a smiley face. Have a smiley face. Have a smiley face. Good job.
Where's my smile?
You can have one too. Well,
Would it be 3.7? Because it's 1.8.
so sig figs are logs have their own rule for sig figs
Oh, logs have a different rule. Oh,
that I kind of just ignore teaching because it's not
are they
worth.
gonna be peaky?
So keep in mind with sig figs, only 1 point out of 100 they actually grade on sig figs.
Oh, okay. So if I get 6 fix wrong, all of my wrong.
You're gonna lose 1 point overall.
Oh, okay.
So
Womp womp.
to me, it's like you think about it, but you don't stress about it.
Oh, I stress every night and day.
About sig figs.
Shouldn't it be 0.0001? That's
Oh, not quite. What went wrong?
3.7. Wait. Isn't that 3.7?
Oh, you just added an X, or you lost a 0.
Oh, so it's
Because that's 0.0001. So that's your salt, right?
yeah.
So that should be on top. Oh no, wait.
Wait, is it like this?
Oh, you have it backwards.
Oh, okay.
This, yeah. So
Oh,
because the
see, you
Na
were
one,
right.
so salt goes on top, acid on the
I
bottom.
just put it in like that.
Yes, that's what you should do. Have a smiley face. Well done. Have a smiley face. Good job, guys.
Is sig figs? Is it 1?
So, long answer. Logs have their own rule for sig figs, which is completely different, and I just don't teach it to you guys because it's just something we shouldn't stress about. So I would just, whenever doing pH, because pH is always going to deal with like taking logs, I would just always keep at least one decimal. So like 3 point something. So, yeah.
My bad.
Yes, have a smiley face. Okay, who have I not checked yet to make sure you got it right? Anyone? Who have I not checked? I need to get my little markers on my desk I'm going to use to help us track. Yes, good job. Have a smiley face.
You got the same thing as us.
Okay, questions on that type of that equation? Good. Have a smiley face. Same around? 3.74? Good job. Okay, take a look now at this example problem. It's the same overall question, but our approach is different. Obviously, what was our last type of buffer? What were the two things mixing?
Salt and sweet.
So whenever it's a salt with a weak, it's pretty straight up. You just plug in the salt on the top, you plug on the acid or the base on the bottom, solve it.
Yeah.
It's a little bit different of approach. We're still going to use the same equation, but the approach is a little bit different when it is a weak acid and a strong base, or vice versa. Okay? The idea here is this. So write this down with me, everybody. So we have here weak acid, CH3COOH, has a pKa of 4.76. A solution is prepared by mixing that amount of our acid with that many moles of our base. Calculate the pH of the solution. So it's still a buffer. We're still going to use pH equals pKa.
Sorry, B.
But the difference is the amount of A minus and HA aren't as straightforward because these two things are going to react with each other. So we're given starting amounts, but we need ending amounts. So rice, yep.
I literally did the same exact thing.
So make a note, the reason why we're using rice is why? We don't know the end amounts. So whenever it's a strong, weak combination buffer, you have to do a rice chart. Okay? All right, so the reaction is the acid. So we have our CH3COOH. It's going to react with our base. Now, our base is NaOH. For simplicity, we can, though, exclude the Na. Because in terms of a buffer, Na is always going to be a spectator every single time. So I'm just going to write OH minus, because that's really what's going to react with the acid. So keep in mind, whenever you're talking about a strong bases, you only care about OH. Strong acids, you only care about H+. The other half of the strongs, you can always get rid of. Okay, so when this reacts, what's the acid going to do? What do acids always do? Good, so it's going to give up its H, so it's this one at the end, that's why it's weird. Okay, but it's going to make H2O and CH3COO minus. Okay, now as I solve this problem, I am going to be changing colors on purpose. If you want to, if it's easier, just keep writing with your pencil, but then if at the end you want to go back and highlight, it might help you remember where things came from. Okay? All right, so we need to plug in our initial amounts into our rice chart, but they have to be in the unit of a mole. So one of them I can plug straight in. I know I have 0.02. Oh, I'm going to change colors here. All right, so I have 0.02 moles of that because that was just given in my problem. But what do I know about my acid?
It's in molar.
Yeah, so we're in molarity and volume, so we got to convert to moles. So I'm going to change my milliliters to liters by moving the decimal over 3. So we're going to get 0.5 liters. So I just took this and changed it into a liter. And then I'm going to times it by the molarity, 0.150 mole per liter. So volume times molarity will cancel out liters and just give you moles. Plug that in. What do we get here? Thank you. 0.075, which then that can go down under our acid. Yeah, Emily.
Even though we like took away the NA, how is it still 0.02 moles of the NaOH?
What do you mean we took it away?
Like we don't have the NA in the equation, but it's still 0.02.
So if I have 1 mole of Na and it breaks up into NaCl, I still have 1 mole of Na and 1 mole of Cl. It's the whole idea of how like moles are not like additive because it's just a counting amount, right? Where just because it splits into 2 things, if you count them, you're still going to have the same amount. Like maybe this makes more sense. Like if I have okay, this is NaOH. As NaOH, how many of them do I have? 1. How many NAs do I have?
1.
How many OHs do I have?
1.
So if the original was 0.2, even though it breaks apart, because that's why we got rid of the NAs, because it breaks apart and it's just spectating, I still have 0.2 moles of the OH. 0.02, thank you. Does that clarify that? Good question. Moles are weird like that. But yeah, Jack.
If you keep the NA in the
Yeah. No, you still could totally keep the NA.
Just for synthesis.
It just helps us, because what are the 2 pieces we're trying to find in our buffer? What do we need to isolate the amounts of? Yeah, we need HA and A minus, right? So this right here, this is my HA. Which one is my A minus?
CH3.
That. So by getting rid of the Na, sometimes it helps you see that better. Without the Na there, you can see the A minus better, but it would be the same. Okay, any other questions before we continue? All right, initially, how much of my products do I have? 0. Now, when you have, and this applies technically to any rice chart, if you only have reactants and no products, and you know the amounts of both, and once again, this is not an equilibrium because they're just reacting with each other, the change is always going to be the one that runs out first because they're going to react and it's going to go away. So which one is going to run out first? Yeah, so the OH. So our change is going to be minus 0.02
Oh, that runs out.
because all of it is going to react because there's less of it, which means this one will change by the same amount. Now, technically, I don't really care about the water, right? So we're just going to ignore that. But then what would be the change of my
Plus 0.02.
choo-choo? That's what people nickname that compound. You see it? Get it?
Sure.
So this would be plus 0.02 because it's a 1-to-1 ratio. Carry that down, so we get 0.02 of this. No more OH minus, which it should always be. The strong substance is the one that always goes away completely because that's not what makes the buffer. It's the weak one that does. And then I'd have left over
A minus
0.055.
No.
Everyone okay there?
Yeah.
So now I can do my equation. So pH is going to equal. This one, notice, gave me the pKa, so I don't even have to take the negative log of it. So we're going to have 4.76 plus the log of 0.02 over 0.055. And when I typed that in this morning, I got 4.32. Questions on same equation, but we had to do a little bit more work to get our HA and our A minus. Once again, if you want to go back with a highlighter, the things that match in color are showing you like where I got these numbers from, right? Like where that came from and where that came from. Yeah, Jack.
When is there like a specific time you don't use the rice chart?
So if it's a salt weak buffer, you don't have to use the rice chart. Whenever it's a strong weak, you always have to use it. Because the key thing is it's like we have to figure out how much A minus is being made. So with a salt, we're just purely dumping in the A minus. So, all right, any before I have you try the next one? Okay, for another smiley face today, try practice 8.9b with your table. Raise your hand if you need help or once you think you've got it. Okay, ready, set, go.
What's the original for hydrofluoric acid?
HF.
That makes sense.
Yeah, you probably should have said that. Hydrofluoric acid, by the way, is just HF is its formula. I should have given that to you as well.
So it's gonna give it to
HF is hydrofluoric acid, right?
So it's a weak acid and a strong base.
HF plus OH minus, there's no NA. What are we making?
You got they're already in the lyrics. I'm gonna see if I do switch and then do we get the same answer?
Actually, that did make sense.
So this isn't a salt.
It's not?
No. Because remember, if it has OH, then it's a strong base, most likely. So that means you have to do a rice chart. Or in a sense, not so much the rice chart, but you have to think about how much is reacting and how much you'll have left, which is a rice chart. It is. Good job. Have a smiley face. Well done.
So then it would subtract 0.4 from everything, right?
Bro, this thing is broken.
No, it's not.
Get it? Broken.
For both, right?
That's not broken.
And then,
I know.
is it correct?
Yes.
Okay. Wait, why?
Because the wait, 0.04? Because the acid and strong base makes the salt pH equals the
It's like real close, but like not the answer.
We're not associated.
I'm wondering if it's just a calculator type, maybe.
Maybe.
Is that the right equation?
I don't.
Oh, no.
I mean, you do take the negative log of that. Let me go look at. Let me go check if something's off with your moles, maybe.
Well, let's see what
You did? Okay. You caught your error.
That's the
Yeah, Garrett.
This one, when there's like the same amount of the acid and the thing.
Uh-huh.
So like, I got 0 for the HA. So what? I think. I don't know,
So-
I'm kinda lost.
That's where think back. So we did 2 different ways we solved this question.
Is it just for the salt?
Is it a salt or is it a so that's the key thing is this one is a salt, and so you don't have you just plug in the
Yeah,
values.
originally I did that. So I guess.
Yes. So the rice chart's only needed when it's the strong mixing with the weak.
Weak.
Yeah.
So this one.
That is it.
So this one is like weak and strong. So I
There you
would
go.
do
So
that.
this one now you have to do the rice chart for, or think about how it's changing. Good job, Daniel. Have a smiley face.
Oh, let's go, Danny. Good job.
Good job, you two. That looks good. Sophie. Not quite. Let's see. Everything looks good though. Just type that in again. Maybe something just.
That's what we all got that.
You all got the same thing? Well, then obviously there's some.
Something's.
One question. Do we just not pay attention to this? Like,
Yep, because in terms of a buffer, these are what we're caring about.
Yeah.
It's kind of the fact that this doesn't affect the pH.
yeah, so like why do we just care about these?
Because those are the two things that are influencing what the pH is at. And we're trying to find the overall pH.
Oh, is it just because, so does the strong base not influence the pH?
Because it reacts completely.
Oh, so since it's all dispersed and it's not like,
Yep.
okay.
In a sense, it did, but once it's reacted, it's not there anymore. Does that make sense?
Yeah.
Okay, how did we all get the same wrong
I
answer?
don't know.
Because then
I don't know, like, does this, yeah.
That's what I mean.
wait, is it 0.0?
Oh, plug that in again. No.
Is it 0.0? Is it 0.0?
Let me look at mine. I think there is a 0. Yes, that's where you're off. So it should be 0.09. Fix that. Okay, what do we get back here?
You don't have calculator right.
Does it have something to do with the milliliters or self-regulators?
I mean, you have to use those to convert to moles. Did you do that? Or did you just take the molarities as they were? Oh, it looks like you just took the molarities as they
Yeah,
were.
because I convert. I thought you were supposed to put similarities into it.
No, you have to put the moles into it. So on this one, it gave us moles, but that's why this one we had to do this step
That makes sense.
to get to moles. So logic-wise, of how you use the rice chart is right. You got to get to moles first. Okay, how'd this table do over here? Nope, but you had the same thing they did. You just lost a 0 or somewhere.
Okay.
This one, it should have been 0.09.
Oh,
I don't know what we typed in wrong, but
0.3 times 0.3 would be
yeah.
0.09. So then
0.3 times 0.3.
0.09 minus 0.3.
How are you two doing?
You were right.
We just got that.
Negative answer.
Oh, so we know something's wrong there.
Yeah, 1 point.
That's what we.
Wait, so what's this number?
Maybe I did 0.
Yeah. 0.09.
Okay, is that the whole thing or just the first part?
86. Whoa.
You should jump on the table and do it.
1.8.
What is going awry here? Because these are the right. Because I know it's like.
Is it the one from two?
That's what it should be.
Well, is it the one from two of them? Or
Because, yeah, we're only focused on the F minus. So it's just. Yes, we don't use the other one.
and is it on the top?
Yeah, let me double check out mine real quick. Oh, look at this choreography over here. Yes, that was my face, guys. Good job. 1.8. I'll be back. Don't worry.
Did I get something?
Something
I
is
didn't
off.
really know what to plug in right here.
So how did you get these numbers?
Well, doesn't the OH converted to these stuff?
But beforehand. So like the
I-
0.1 and 1.
I converted.
Oh, you have it backwards.
Oh, I do.
Because it's moles per liter. So it should be 0.3 over liter. Fix that and then it should be. Where am I looking?
Sorry.
Yes, that's the answer. Good job.
Is it 1.8?
Yes, it is. Oh, that was my Oh, he's teaching you guys.
He is.
Okay. Welcome. What do we get over here, people?
1.81.
That is it.
We were productive, I promise.
Yours is slightly off.
Yeah, I got it.
Which is probably just maybe a small check. Oh, you plugged in the molarity. But we got to convert. You only converted one of your moles. Do you see that percent?
Oh, do we have to?
They both have to be in mole form.
For rice charts, it has to be.
Yes. Yes. Okay, how are we doing over here?
1.81.
Good job. How is my face? Okay. Okay, what do we get over here?
1.81.
Yes, good job. Have a smiley face, guys. Okay. Did everybody get our answer? Did we get there? All right, what about you two? Yes. Do we know what went wrong?
I just
Just a
retyped it.
calculator thing?
Yeah.
But so setup was good then. Have a smiley face, guys. Okay. Eyes up front here, everybody. Wrap up on buffers and we'll be done for today. So on your homework tonight, just word of caution to put into your brain.
I'm cautioned.
Make sure you pay attention to, is it a salt weak buffer or is it a weak strong buffer? Because once again, we use the same equation, pH equals the pKa of the A thing, right? But whether or not you have to use a rice chart to get you there varies. So that pay close attention to that on the homework tonight, okay? All right, last two little pieces here. Topic-wise, we're jumping to 8.10 because it's still about buffers, so I just want to talk about buffers all at the same time. We already mentioned this, but just to close on buffers today, buffers have a capacity, right? You can't infinitely just pour acid into them and they always maintain the pH, right? Eventually, what runs out? If I'm adding acid in, then you ran out of A-. On the base side, I'd run out of HA, right? So the problem is it's the HA, right? And the A- are what we need for a buffer solution. And so the problem is if you run out of these, right? If these go away because you've added so much of the other, then in a sense the buffer has hit its capacity and it breaks, meaning the pH will drastically drop or drastically shoot up. Okay, so to maximize buffer capacity, it's about just having as high of concentration of both of these as possible, or as much as you need, right? So if you were trying to pick, there's one homework problem on your homework tonight that talks about which of these has the greatest buffering capacity. It's purely about which one has the highest concentrations of both pieces. Because you don't want just high of one, because that means it only can buffer in one direction, okay? Does that make any questions about what buffering capacity is? Okay, now we talked about how to make a buffer, okay? Now, in terms of if it's just shown to you, now if you are looking at to create a buffer of a specific range, so this says we want to make a buffer with a pH of 4.55. These are our acids available to pick from. We would then add a corresponding salt or strong base, and we want to know which one is going to be the best choice. So this is a key thing to highlight here, everybody. When you're trying to pick your substance to create your buffer, you want the pKa to be as close to the pH that you're trying to buffer. Because if my acid naturally exists at a pH of 3, I can shift that a little bit, but it's going to be really hard to get an acid that is a pH of 3 and get it to change to a pH of 7. So you need to pick something that's already close to the pH you're trying to buffer at, okay? Now the way we do that is by calculating the pKa. So we could plug into our calculator the negative log of all these numbers. But I'm going to show you really quick for multiple choice sake to save you some work of how you can estimate a log. So the way to estimate the negative log of this number is by looking at the exponent and saying it's always going to be in the range of that's the highest it could be and one less. So this pKa is going to be between 4 to 5 because of the power to the 5th. This one would be between 3 to 4. And our last one would be 6 to 7. So which acid would I want to pick for my buffer? Yep, the first one, because I want 4.5 and that falls within my range. So I would choose to use acetic acid and then I would add a certain amount of salt to get us there. Does that make sense on like how to pick the right substance for a buffer I'm trying to make?
Yes.
Okay. Any final questions people have? We got like 90 seconds left.
Can
in 90 seconds.